So what will be covered in this course? What is not covered? This is not covered. Okay, what will not cover in this course will be those graphic software. Okay, like CAD, computer aided design, Photoshop, or any painting tools, 3D Studio Max, and other modeling tools like Maya, Blender. All these graphic software will not be covered in this course. Okay, we are learning the low level. Okay, using Microsoft Visual Studio with C++ programming language and graphic library OpenGL to create our graphic. Okay, so you can build this software in future. Okay, and you will not be assessed with your artistic skill. Okay, no need to draw or how put it your graphic that you produce is not so important, but you need to produce the graphic. Okay, the functionality is the one that you have to concentrate on. Okay, and you wouldn't game design. This is not a game course. Okay, you are not necessary to create a game. Okay, you actually create a 3D interactive application rather than a game. Okay, assessment. The first time see me, haven't have class with me. This is the programming heavy and coursework heavy subject, 70%. Okay, just now don't have projector. Now you can see this. Okay, it's in your week 1 slide. Okay, 70% coursework, 30% exam. Okay, exam 2 hours paper, 4 questions, 100 marks. 70% coursework break down to 3 components here. So the first one will be your assignment. It's a group assignment. Okay, 2 to 3 people, 60%. And then practical assessment or practical exercises that you're going to do every week. Okay, after your practical class is 20%. Then midterm test, 20%. Okay, we schedule on week 8. Okay, after finish half of the syllabus. Okay, chapter 1 to 5. So will be tested on your midterm test. So this 100%, okay, will comprise to 70% of your coursework. Okay, so you have to work hard throughout the semester for your coursework. So we will use OpenGL as a graphic libraries or API. Okay, in these subjects. Okay, because it's device independent, you can use in whatever hardware. Okay, your PC, your tablet. Okay, any machine. Okay, or your mobile, and it also platform independent with whichever OS. Okay, Mac, Linux, Windows also support OpenGL, and it is open source, free. You don't need to install it separately. So it comes together with your Visual Studio, Microsoft Visual Studio. Okay, reside in the Windows SDK. Okay, Windows Development Kit. Okay, unless you go and install, you go and uncheck the SDK. Okay, else OpenGL will be inside. Okay, and the language we use will be C++. Okay, in chapter 1 is very simple. Okay, just some introduction. Okay, we will just cover these 2 things. Okay, you see some of the example application that we have that use computer graphic. Okay, if you heard the term CG, CG, Miss also will use like CG mean computer graphics. Okay, you will see a lot of CG movies, a lot of CG applications mean computer graphics. Okay, and we look at some of the brief histories, how this CG evolved. Okay, until now. Okay, CG already widely used in design. Okay, use the computer to help you to design whatever things. Okay, the products. Okay, any products. Okay, that you can just create in the computer first before you actually build the product out. Okay, and you can see different angle, 360, different view, and then it also can do measurement. Okay, you can see can do measurement. So widely used in architecture as well, quantity survey, QS. Okay, it's also used in engineering analysis, lots of areas. Okay, with this one, that is more easy for you to see. Rather than draw on the paper, now everything on your screen. Okay, you see all the graphic on your screen. Okay, so you don't like to see this. There are a lot of formula here. This one your miss will be dizzy already. Okay, then I show you this. Better, right? Okay, so you imagine how the molecule look like, how the DNA, okay, rather than give you all the formula, all the, just now you see the stump. Okay, then you can see in the pictures. Okay, graphic represent downwards. Okay, rather than pure imagination, you know how it looks like. Okay, show you the graphic. Okay, it's used in science. Okay, many different areas. Okay, simulations. Okay, one of the area that use CG will be the simulations of effects. Okay, whatever effects. Okay, whatever simulator that you can find now, it actually is around us lah. Okay, everything. Even though your mobile, you can see a lot of CG in your screen. Okay, in our daily life. Okay, and data visualizations. Okay, now people talk about big data, data science. Okay, you don't want to see all the data in table now. You want to see the data in graphics. Okay, process all the big data. Okay, in graphic like the flags. Okay, on the radar, on the sky. Okay, just show like this. Rather than you see all the text. Okay, and you can use like graph, bar, or chart. Okay, graphics to represent the data. Okay, data visualization is very important. Okay, one of the areas that use CG a lot. Okay, medicine. Okay, now you go to do X-ray. Okay, your doctor didn't print out the whole hard copy of X-ray for you already. You ask you go and see the screen. Okay, everything is on the screen. It's in the computer. Okay, so medicine also widely used CG. You can see very clearly with different angle what is happening on the human head here. Okay, all the crack. Okay, with the use of the computer graphics, and also widely used in architectures. Okay, the building, the floor plan. Okay, before we actually build the building up, okay, do it in your computer first. Okay, then you can study the feasibility. Okay, anything, is it look right? Is it feasible to be built? And then you can see nicely. Okay, how it look like? Okay, look and feel. Okay, before you actually create it up. Okay, it's also save time and save cost. Okay, save time rather than you buy a lot of things and do, and then at the end it fail. Okay, you can save the time also. Okay, product design, same thing lah. And then it's also used in animation. So a lot of CG movie nowadays, pure animation. Okay, this one old one lah. Okay, Lego movies. Okay, special effect. This one long time ago. History. Okay, how people want to do this effect? Go and make up your style, become green color, and then only you can create this effect. Okay, now no need lah. Use PC. Okay, use CG to do. Do this. Use CG to do can already. Save time, save cost. Okay, advantages. Okay, why people use CG? Okay, no need to exactly go and kill the people and fight. Just use the CG to do. One people do like this, another people do like that. Just combine. Okay. So that's why now you can have a lots of good movies now. Okay. Like Avatar, go and watch already. Two, very nice. Okay, a lot of CG being used inside. Okay, those a lot of CG movies that very good one. Special effect. So special effects let you to do the things that cannot achieve in real life. Like the building explode, not really explode one. You explode KLCC still there. Okay, you see in the movies, the whole building collapse, and then the whole building is still there. It's just use CG to do. Okay, that you can go to other planet. It's not really you go to other planet. It's just inside the CG. Okay, like the Star Wars. Okay, you are in the outer space. Not exactly to go to the outer space. You just do like whatever magic, those things. Okay, real life there's no such thing, but you can do using CG, special effect. Okay. This one show you some history of CG. Okay, before this, how the Iron Man look like. From here, change until here. Okay, there's improvements of the CG. You can see from here. Okay, graphics of computer. So last time, all time, your Miss PC, There's no graphic, there's no window. My time no window. Okay, only text. Only text. So I want to copy and paste, I need to type command. MC copy from C dot where to where. Okay, I cannot right click copy and then right click paste. There's no such thing. Okay, and PC there's no graphic. So that's why we okay, so CG also widely used in games lah. Okay, this one everyone know. Okay, so this one history of the games last time. Okay, we now go to the, okay, you see evolution. This one is the color changing. Okay, last time we only had black and white. Okay, 2-bit color, 0 and 1. Then we have a slowly better, okay, 16-bit color. 16-bit color change for, okay, now we have how many? True color full HD. Okay, 32. You can use the more improvements of the graphic. So history. Okay, so the CG is started by these guys. Okay, the father of CG. Okay, in 1963. Okay, that used the sketch patch. Okay, this machine you see so big. Okay, to draw on the screen to create the graphic. Okay, to create this you need to have big machine like this, so big, and the whole studio with all the equipment. Now need to create this kind of graphic with only black and white. In 1969. Okay, with this 3D picture system that draw black and white. So then in 1970 there is an improvement to start to have colors. Okay, but you only have the main colors lah, red, green, blue, RGB. Okay, with raster graphics. Okay, means support pixel already. Vector. Okay, with lighting, curve, textures, so you can create this kind of graphics in 1970. Okay, then 72, then we start to have the old school games with the big arcade machine like this, just to play a simple Pong game with black and white. Okay, for the video arcade games in 1972. So then another big milestone or achievement in CG will be in 1918. This one is big improvement. Okay, we start to have global illuminations. Mean the lighting, you can know the ray is cast from where. Okay, the ray casting to create this photorealism effects. And from this era start to have digital camera. Okay, before this you want to take pictures, it's the big camera with the film, and then you have to wash out the hard copy. There's no picture on the screen, no. You miss time, no. Okay, last time I took the big camera with the film and then take picture and have to wash out. I cannot see my pictures one until I wash out the film. Okay, only 1980 start to have the digital camera. Oh, then you take picture, you can see on the screen there your pictures. So it's at this time because at here then they only achieve this photorealism effects to have the digital camera. So after this, then another 10 more years, 1990. Okay, when you have photorealistic, when people go for realistic already, they will try to go for not realistic. Okay, reverse. This is human. Okay, just like the trend, when you go modern, sometimes you will go back. Okay, so you start to reverse to go to non-photorealistic. Okay, non-photorealistic actually is shell shaded. You just put the outline. Okay, draw the outline. Okay, for the shape. Then you can have this kind of effects. It look cartoonish. Okay, cartoonish style or non-photorealistic rendering. And we have volume. Okay, 3D objects. Okay, volume rendering. so that you have this one shell shaded with the outline, which is called non-photorealistic rendering. This one is 19. Okay, then your syllabus, your lecture slide is only 90. Then we have 2000. Now 2020. Okay, so people go for VR, AR. Okay, 3D, 4D, 5D. Okay, so now we look at augmented reality. Take the model out. Okay, augmented reality and virtual reality. Okay, touch. Okay, use the Oculus and then touch. Okay, interaction. Okay, so the more advanced one you see in the movie one, I will not. Then you walk like this, then you can just touch, then you can just go to another side. Those things haven't. Okay, so these are the evaluations of the computer graphics. We can achieve more. Okay, it's still improving now. So you can see the latest CG. Okay, what are the people go for is the shading effect. Okay, the directions of the light, the changes of the appearance of the model. Okay, shading, which we will learn in chapter 10 later. Okay, to make it really realistic, the whole model. Okay, that's what we try to achieve lah in computer graphics. So that's basically chapter 1. Okay, not much. Just see some applications of CG used in various field or areas, and then what are the advantages, disadvantages, and then we look at the brief history. Okay, don't worry, history I won't test you. Okay, history we won't come up in your exam or your test. Okay, history just to share with you. Okay, so the most important in chapter 2. Okay, we start to go in technical. Okay, also not technical. Practical will be chapter 3. Okay, your practical one, your practical one is chapter 3. Okay, chapter 1 or 2 is just to let you know the graphic backlines. Okay, how you see from the real world. Okay, this is your real world. I see you in 3D. Okay, when I see you in the screen, you are 2D. Okay, your pictures on the screen is 2D. Okay, I take photo. Okay, take your pictures. I see you real, you are 3D lah. When I see your picture on the screen is 2D. So how from your 3D come here become 2D? Let's go through your graphic pipelines. Okay, your graphic pipelines happen in your graphic card. Okay, so this course you need to have good graphic card. That Yami already told you, those that have class with me just now. So what we will learn in chapter 2. So don't worry, your chapter is not so long because we have 1 hour lectures only. Okay, chapter 1 is the shortest one. Okay, and chapter 4 will have 2 lah, part 1 and part 2 may need 2 weeks, and also texture need 2 weeks to cover. Okay, the rest can finish in 1 hour. Okay, so chapter 2 we will see graphic API, application programming interface, okay, which is your OpenGL. Okay, your graphic library. So other than OpenGL, we also have DirectX. DirectX is also another graphic library. Okay, this one DirectX you not learn. ST student will learn. Interactive software technology student will learn. They learn during their diploma. And OpenGL, they come to degree, they will learn with me lah. It's also a graphic library, but DirectX is have to pay. It's not open source. So graphic pipelines, so we speak to fixed and programmable. Okay, fixed means you cannot change. Something that you cannot change, your graphic card will do the job. Okay, programmable is you guys, programmer is the one that can change the application that you do. Okay, to change what you want, how you want the graphic to be look like. So what is API? Okay, application programming interface. It actually is consists a set of functions. Okay, Okay, it's actually graphic library classes. Okay, classes. Then you can just use, okay, in order for you to communicate with your graphic card from your program, your graphic card until your what you can show in your software, your screen. So common graphic API, we have OpenGL and DirectX. Okay, DirectX is under Microsoft, so it's licensing. So we use OpenGL, okay, it's open source. So it's a low-level interface to your graphic hardware. So it's actually as a bridge in the middle to communicate your program. This is what you will be written later. Okay, your program, your OpenGL program that you write. Okay, then to communicate with all your hardware. Okay, your graphic card. So use your keyboard and mouse for the input, and then to produce the output on your screen. Okay, so between your graphic hardware and your application program. So there are a series of OpenGL libraries here, or classes. So we have GLUT, okay, GLU and GL. So we will start to learn GL first. GL is the low level library. Okay, GL. Then your miss also will teach GLU, your practical class. Okay, it's a little bit higher. Okay, for complex objects. And then we have this GLUT. Okay, this one GLUT, I didn't teach. Okay, I don't teach in this course. It's for window management, keyboard, mouse. Okay, input or menu. So if some of you want to use your style in your assignment or in your practical, it's optional. It's up to you. Because some will say, Miss, I want to render text on the screen, on the window. Then you need to use GLUT. Okay, what I will teach you is only window input and then GL and GLU library. So these are all these graphic libraries. So communicate between your application program and your graphic, your hardware. Okay, let's see what is 3D graphic. Okay, is this 3D? Yes? Yes? Why you say it's 3D?
Like 3D.
Okay, is this graphic 3D? Yes, no? If you say yes, why you say it's 3D? If you say no, why you say it's no? I don't know. Miss tell.
You only can see front.
Okay, what give you the sense that you say this is 3D? But first of all, you have to know what is 3D. 3D stand for? Three dimensions. So what you have there? Okay, the 3 dimensions is your width, your height, your height, and also the depth. Okay, the depth. So if you see, example, your 2D objects, if the paper, okay, on the table, you don't have the perceptions of the depth. So the most important to differentiate the 2D and 3D is the depth. Okay, the 3rd dimension. So if paper on the desk, there's no depthness, there is 2D objects. So if you see here, it's a can of soda. Okay, it's round. You have your width, your height, and then you also have the depth. Then you say it's 3D. Okay, it's 3D. But how we can actually visualize a 3D world, okay, on the 2D computer screen? Okay, your screen, your screen is flat. Okay, this one flat, this one is 2D. So I show you whatever thing inside is also 2D. But you tell me that is 3D graphic is because they have the illusions of the depthness. Okay, so when you project, okay, anything you transfer a real world to a screen, it will reduce 1 dimension, it will become 2D. So your 3D graphic is actually a 2D images on the screen, but it just gives you the illusions of the 3rd dimensions, which is the depthness. Okay, so how you show this 3rd dimension of depthness? Okay, one of the ways is to use the view, perspective view. Okay, perspective view will give you the illusions of depthness. Okay, if you didn't pair up with the view, you only see the front view of the object, the top view of the object. Even though the object is 3D, you still look like 2D. Okay, so 2D plus perspective, you get 3D graphic. So there's one view we call it as isometric view, or sometimes you will hear people say 2.5D. It's actually referred to isometric. Okay, isometric means you actually tilt up your camera and then you face down, look down. Okay, the object there, the image there are all 2D, but because the view, to make it have the feel that it look like 3D. Okay, this is 2.5D, you can see here. Okay, this view is isometric, 2.5D. So projection is the one to let you to create this 3D graphic in your 2D screen. So this is the real world objects in a 3D. Okay, and then you have your screen. This is your projection plan. Okay, project on the screen. This is how your final image look like. Okay, so if you see the projection line, this is the projection line. Okay, at the end it will actually convert in a single point. This one is perspective view. Okay, so your object, your graphic on the screen will look like 3D. Okay, projection we will go into detail later in chapter 5. Chapter 5. So with perspective and orthographic view. Okay, now we look at the graphic pipelines. Okay, these are the process, okay, that happens in your graphic card. Okay, so from the real world, okay, what we can see from the real world is all the vertex, all the point. Okay, vertices. You call it vertices. Then you go through these 4 components. At the end, what you see on the screen will be pixels. Okay, pixel the dot there on the screen will be pixel. So these 4 components, you need to know one by one what is happening inside, what are the tasks that they actually perform, and you have to memorize, you have to know. Okay, vertex processor. We start with vertex processor. Then we have creeper and primitive assembler, rasterizations, and last one will be fragment processor. Okay, we start one by one. These 4 components are the main component in our graphic pipelines. Okay, if you go online, you go and search graphic pipeline, there are lots of components, because they will break down to sub component. Okay, not necessary to know all these sub. You need to know these 4 main components. Enough. Okay, start with vertex processor. So we need to know what is vertex first. Okay, vertex is actually can refer to a point. Okay, a point, and which will tell you these properties or attributes consist of the location, the color, normal, texture coordinate, etc. Okay, you see like this one, this dot. These are vertex or this point. Then it will carry this information. So in the vertex processor, it will do the transformation where this point should be, the location, the positions of the point, and then what is the color of this point, and then the texture coordinate if you do the texture mapping. So to show this vertex or this point, you can either use object space, based on your origin. Object space means each of the object will have their own origin, have their own space. Or you can use word space, all the objects share one. Okay, one origin. So in OpenGL, we will use this word space. Okay, easier. Okay, you have one XYZ axis, and then you just declare where's your point, your coordinate. Okay, this is what it did in the vertex processor. So after you have all these points, Okay, next is we'll pass to this clipper and primitive assembler. Okay, you already have the point here. This is our text point. So those transform vertices in primitive assembler. Okay, assembler means connect. Okay, it will connect this point. So if you only have 2 points, okay, this one orange color, this one yellow color line. So primitive assembler, okay, will connect it to make a line. Okay, this is a job of primitive assembler. Okay, how the vertices will be connected together to make up a primitive. So if you have a triangle, then you have 3 points here, and then you will connect them to form a triangle. Okay, this is what the job of primitive assembler do. Just connect all these vertices. Okay, then clipper, okay, will remove or clip against or eliminate those unwanted vertices that is outside of your viewing volume. Okay, this is your viewing volume. So you see the head of the count is outside of the viewing volume. So this, all the vertices here will be clipped up or removed. So it won't process, it won't send to the rasterization to process later. So we will only process all the vertices that we can see inside the viewing volume. Okay, how to define this viewing volume? We will use projection. Okay, and we will learn detail in chapter 5 later. So click again the viewing frustum. Frustum means viewing volume same. Okay, so after you have all these vertices, you pass to your rasterizer. Okay, rasterizations. Okay, the rasterizer is the one that convert your vertices to pixels. Okay, this one happen in your graphic card. The frame buffer is the one that doing the job. Okay, from the raster to the vector graphic. So it will determine the fragments. Okay, fragments mean a group of pixels, and the pixel positions of the primitive, like this one. Okay, just now the line, this one draw a line. Primitive assembler already draw a line. So in the rasterizer, it convert to pixel already. So you have 6, 1, 2, 3, 4, 5, 6 pixels here. Okay, this one is the job of rasterizer. Okay, so this is called one fragment. This is called one fragment. Okay. So a piece of data that will be used to update pixel in the frame buffer. So contain color, normal, and texture coordinate. So this one in the rasterization, there is no color for the pixel yet. Okay, it's already converted and it's kept in your frame buffer. Okay, and it will split outside and inside. Rasterizer will determine which pixel is inside the polygon. Okay, with the color, and which one is the background. Okay, this job is done in the rasterization. Okay, so last then it will pass to the fragment processor. So what is frame buffer? Okay, frame buffer your graphic card. Okay, your graphic card actually got a lot of buffer mean temporary. Okay, to keep your fragment, your pixel. It will keep here before we actually display on your screen. Okay, so inside your frame buffer, so the fragment will be processed in the fragment processor. So interpolate the color informations like this one. This point is yellow, this point is orange. So you interpolate. Okay, these 3 become orange, these 3 become yellow. Okay, it will interpolate, mean take the average and update the pixel in the frame buffer. Then before it display, it will do these 3 tests. Fragment processor, it will perform these 3 tests. Okay, depth test, alpha test, and stencil test. Okay, so what is depth test? Okay, it will test again the Z value. Which pixel is in front, which pixel is behind. Okay, hidden surface remover. This one. Okay, so the back pixel shouldn't be rendered. You only see the front face. The one at the back you cannot see. So the back pixel should be removed. Don't render on the screen. That's the job of depth test. Okay, then we have this alpha test. Okay, this one is for blending. If you have 2 objects, different opacity, different transparency, like the window, the door, the glass, You can see the glass pixel is render, and the object outside pixel is also render. But this one 30%, this one 70%. So you render the opacity 30% of the glass pixel, okay, 70% of the object outside. Transparency blending, you can see like this one. Okay, still can see the object there. There are 2 pixels are active, and you test on the alpha test. Okay, color alteration due to texture blending and transparency. Okay, that's alpha test. And last one will be stencil test. Okay, stencil test is for masking or shadow. Okay, you want to remove those unwanted pixel based on certain masks. Okay, masking or pattern. Okay, stencil test is very widely used in shadow. Okay, when we learn chapter 9, we will see stencil. Okay, what is stencil test and how it's going to remove some of the pixels that which you shouldn't be rendered. Okay, then at the end, okay, after done the 3 tests, okay, update all the pixel in the frame buffer, then you can see your final display on the screen. Okay, how the graphic look like on your screen. Okay, these 4 components are Vertex processor, clipper and primitive assembler, rasterization, and fragment processor. Okay, then display the final image on your screen. Okay, this one is the summary. Okay, summary. You can see the start with vertex, dot, dot, dot. Okay, point. Okay, primitive assembler. Okay, connect. Okay, so a clipper remove the dot that is outside. Then this one is rasterization. Okay, from vertices now become pixels. Okay, this one put colors, interpolations, and the 3 tests. Fragment processor, the job of the fragment processor, and then this is what you see on the screen at the end. Okay, so this will be our graphic pipelines. Okay. Can I enough time or not? Okay, so why we need a programmable graphic pipeline? Okay, because we want to achieve good quality of graphic. Okay, you want your graphic to look good and realistic. So you have to program. So if don't program, then you cannot achieve good one. This one is old one. Okay, you want this right? You don't want this right? That's why you need to program more. Okay? You want this. Now you know why. Okay, you want this, you don't want this. Okay, you want to achieve good quality of graphic, then you have to program. That's why we have some graphic pipeline that you can program. Okay, so we have 4. This one just compare the detail. Can program, not program. You want this or you want this? This is your job. This is your job. But now your assignment, you give me this one because you are a student. Okay, this one, the graphic pipelines, okay, is actually reside in your hardware. Okay, you see this is your applications, the program that you write, okay, to communicate with your graphic system here, your graphic pipeline here. You're using this API, your OpenGL or DirectX, okay, library, graphic library. So this is your hardware, okay, your graphic card, so it will be your graphic pipelines here. Okay, so you have your vertex processor. So these 2 will be the one that you program. Vertex processor and the fragment processor. These 2 are programmable. Okay, your job. Vertex and fragment processor, the 2 processor. The middle one, okay, primitive assembler, rasterization. Okay, these 2 is fixed function pipeline. You didn't program. Okay, the graphic card will convert the pixel, the vertices to pixel rasterization and connect your vertices. These 2 you didn't program. Okay, our job is to program these 2. Okay, this one frame buffer. This one your front end GPU, your graphic card front end. Okay, you can see here all is your vertex. Come here, then come here will become pixel. Okay, so the most important component will be this one, these four, vertex processor, primitive assembler, rasterization, fragment processor. Okay, this is your boundary between your CPU and GPU. This is your GPU. GPU means your graphic processing unit. Okay, your graphic card. Okay, this one is to change the diagram. Okay, to programmable unit. Okay, you look at these two, fragment processor and vertex processor. These two are the ones that are programmable. Okay, in your graphic pipeline. Okay, fixed one, rasterizer, primitive assembler. Okay, so from here you can see start is from your, this one is your memory, your hard disk. Okay, your hard disk. Let's start from your vertices. Okay, all black color vertices. Come here, primitive assembler. Come. Rasterizer. After the rasterizer, this one rasterizer. Okay, all these gray color one, this one are fixed. Okay, fixed. Fixed graphic pipeline mean fixed means fixed. You cannot program. Okay, it will do the job on its own. Okay, after this rasterizer, all the black color vertices will change to pink color. Okay, or purple. Okay, this one is fragment. Pixel. Okay, pixel, and then use your frame buffer. Okay, frame buffer also memory, temporary memory to keep your graphic. Okay, before actually display. Okay, green color will be pixel group, and then if you go to texture mapping, this one texture memory, so you can code. So it will be in the two processor here. So this one your chapter 7. Okay, texture mapping we will do. Okay, so the rest of the this one you don't need to care lah. All these are fixed. Okay, the gray color one all are fixed lah. So we are only interested on these two. Okay, that your job that you can code later or you can program later in your application. So programmable vertex processor is the hardware unit that run your computer graphic vertex program. So when you program the two processor, whether you want to code by vertex or want to code by your fragment, so it's up to you. So you see the improvements. Okay, improvement of the graphics with shader. This one Metal Gear Solid lah. Okay, last slide. Okay, comparison between your CPU and your GPU. Okay, CPU your computer processing unit, and your this one your graphic processing unit GPU, your graphic card. So your graphic card is reside in your CPU. Okay, so your CPU will do the rest of the system job. Okay, you have a lot of software. Okay, your application, your DirectX, your driver, your software, and your hard disk is system memory. For your graphic card, it will only deal with everything on the graphic. Okay, it will be your video memory, your images, your video, your pictures. Okay, we will keep in your graphic card, and then here will be your graphic pipeline. Okay, vertex assembler, primitive assembler, rasterizer. Okay, texture, shading, everything, pictures, it will be processed here. So all the graphic tasks will be handled by your graphic card. Okay, the rest of the system tasks will be done by your CPU. Okay, so when you ask to compare CPU and GPU in graphic programming, you compare this enough already. Okay, do not compare in other aspects like networking, which one faster, which one easy, which one big. With support streaming, which one not support streaming, okay, not necessary. You just tell all the graphic tasks is done by your GPU. Your CPU is in charge of the system tasks. Okay, and inside your graphic card must mention, okay, is your graphic pipelines that will convert from your vertices to your pixel. That's the job of your graphic card. Okay, your GPU. And then your memory here for GPU is your video memory, and your CPU is your system memory. Okay. So these are the comparison CPU and GPU. So we need good graphic card this course. Okay, so that's all. So for chapter 2, so now you should know what is API. Okay, it's actually a graphic library with a sets of functions. Okay, graphic function that you can use to communicate your program with the hardware. Okay, and graphic pipeline, how you convert from vertices to pixel, the 4 main components. What are they?
Vertex.
What are the 4 components in our graphic pipeline? What processor? Text processor, primitive assembler and clipper, rasterizations, and also fragment processor. So the 2 processor, vertex processor and fragment processor, will be programmable. Okay, the one that you can program. Okay, the fixed function pipeline will be the middle 2, primitive assembler and clipper, and also rasterization. Okay, and the last slide we see the differences between CPU and GPU. This is what we have covered in chapter 2. Okay, so any question? Good. Good, Chapter 1 and 2 easy lah.